Hello, welcome back to my study. In this video, I am discussing about real integrals using residues. So, how to evaluate real integrals using residues? That means the integral of the form integral minus infinity to infinity some f of x dx. So, if you have an integral of the form integral minus infinity to infinity f of x dx, and we want to evaluate this type of integrals. So, first we consider f of z. That means instead of x we use f of z, a complex function, and find out the singularities. Finding out singularities of f of z. And now the real line minus infinity to infinity means the real line. We consider the origin 0 and minus r to capital R. This region and the semicircular region from minus r to capital R. So the minus r to R in this direction and R to capital minus R in this direction, means anti-clockwise. So we consider the curve gamma as the line segment from minus R to R plus the semicircular, let it be gamma capital R, the semicircular portion. Gamma capital R, the semicircle. In the upper half plane, we consider half plane, upper half plane, half circle in upper half plane. And now this R tends to infinity. If we consider the limit R tends to infinity, then this is minus infinity to infinity. This will becomes this integral minus infinity to infinity. And the upper half plane and this curve portion is negligible if we put the limit r tends to infinity. That means we got this integral becomes this type, integral over gamma f of z dz, and this we know by residue theorem this is equal to 2 pi I into 2 pi I into residue summation of residues. That means sum of residues inside the region, singularities inside the region. That means if f of z has singularities in this region, upper half plane portion, we consider those singularities and find out residue at those singularities zi. Zi's are in upper half plane. So sum of these residues into 2 pi I is integral. This is by residue theorem. Residue theorem 2 pi. Residue theorem is integral over gamma f of z dz equal to 2 pi I into sum of residue at the singularities inside gamma. So we consider inside singularity. That means singularities in upper half plane portion. Okay. Let us consider an example. So consider the integral minus infinity to infinity x square divided by 1 plus x raised to 4 dx. So we need to evaluate this integral, and this integral value is pi by root 2. So we need to find this integral value. So consider this pi by root 2. Okay. So consider x square by 1 plus x square. Our function f of x as f of z. So that is z square divided by 1 plus z raised to 4. Now find out the singularities of f of z. Singularities of f of z is 1 plus z raised to 4 is equal to 0. The denominator equal to 0. That means z raised to 4 is equal to minus 1. This is fourth root of minus 1. We know that nth root of nth root of a complex number. Nth root of a complex number z is equal to e raised to I 2 pi k plus argument of z all divided by n. This is nth root of a complex number. So we need to find fourth root of minus 1. So that is equal to e raised to I 2 pi k plus argument of minus 1. Argument of minus 1. Sorry, this is small argument. The capital argument denoting the principal argument. This is small argument. Argument of minus 1 means minus 1 is here. So argument of minus 1 is pi. So pi all divided by n is 4. We need to find fourth root. So n is 4. So this is e raised to I. Sorry, this I is common to this. I e raised to I. This is 2 pi k plus 1 plus pi means 2k plus 1 pi by 4. So this is fourth unit. Nth root means k 0 to n minus 1. So here 0, 1, 2, 3. So we get e raised to, putting k equal to 0, we get e raised to I pi by 4. Next e raised to I 3 pi by 4. E raised to I 5 pi by 4. E raised to I 7 pi by 4. So these are fourth root of minus 1. So these are the singularities of this function f of z. But we only need the singularities in upper half plane portion. That means we consider the region minus capital R to a particular capital R. Origin is here. And the upper half plane portion, and minus R to R line segment, and R2 minus R the semicircular portion gamma R. So this is our gamma. This is full closed portion is our gamma. Okay. So we need only the singularities in this region upper half plane. So only e raised to pi by 4, e raised to pi by 4 in first quadrant, e raised to I 3 pi by 4 is in second quadrant. E raised to I pi by 4 means cos pi by 4 plus I sin pi by 4. That means 1 by root 2 plus I 1 by root 2. And this is e raised to I 3 pi by 4. Cos 3 pi by 4 means 3 pi by 4 is in second quadrant. That means only sign is positive. So this gives minus 1 by root 2, minus 1 by root 2 plus I by root 2. So these two are in upper half plane and these are in lower half plane. This is in third quadrant, this is in fourth quadrant. So we only consider singularities in upper half plane. So this is our Z1 and this is our Z2. Okay. Now we need to apply residue theorem. That means the integral, if we consider the limit r tends to infinity, the integral is integral over gamma. Gamma is line segment plus the half circle, closed curve, f of z dz, which is equal to, by residue theorem, 2 pi I into sum of residues in upper half plane. That means residue of f at e raised to I pi by 4 plus residue of f at e raised to I 3 pi by 4. Okay. Now we need to find these residues. First, residue of f at e raised to I pi by 4. So our function f of z is z square divided by z raised to 4 plus 1. Since it have 4 distinct roots, we can factorize this as z minus z1 into z minus z2 into z minus z3 into z minus z4. That z1, z2, z3 are the roots. E raised to I pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. Okay. So all these singularities are symbol poles. So e raised to I pi by 4 is a symbol pole. We know the equation of residue at a symbol pole is limit z tends to e raised to I pi by 4. I call it as z1. So limit z tends to z1, z minus z1, z minus z1 into f of z. This is the equation of finding residue at a symbol pole. Okay, I already uploaded some videos related to residue theorem and finding residue at poles. So this is limit to z tends to z1, z minus z1 cancelled, other terms is z square divided by z minus z2, z minus z3, z minus z4. Okay. Now this is limit z tends to e raised to I pi by 4, e raised to I pi by 4 all square divided by e raised to I pi by 4 minus e raised to I 3 pi by 4, e raised to I pi by 4 minus e raised to I 5 pi by 4, e raised to I pi by 4 minus e raised to I 7 pi by 4. Okay. Now we get limit z tends to e raised to I pi by 4. This is e raised to I pi by 4 all square means I 2 pi by 4. That means e raised to I pi by 2. E raised to I pi by 2 is cos pi by 2 plus I sin pi by 2. We know that cos pi by 2 is 0, sin pi by 2 1. So we get 0 plus I. That is this value is I. Can substitute as I. So this is I. Now minus these terms. That means I already said that e raised to I pi by 4 is 1 by root 2 plus 1 by I by root 2. E raised to I 3 pi by 4 is minus 1 by root 2 plus I by root 2. E raised to I 5 pi by 4 is in third quadrant. In third quadrant, tan only positive. That means cos and sin are negative. So this is minus 1 by root 2 minus I by root 2. E raised to I 7 pi by 4 is in fourth quadrant. There cos is positive and sin is negative. Now minus these terms. This minus this gives 1 by root 2 minus 1 by root 2 is 2 by root 2. I by root 2 minus I by root 2 cancelled. And this minus this gives 1 by root 2 minus 1 by root 2. Again 2 by root 2, I by root 2 minus I by root 2 plus 2I by root 2. And minus this term gives 1 by root 2 minus 1 by root 2 0, I by root 2 minus I by root 2, 2I by root 2. Substitute these values. First we get 2 by root 2, next is 2 by root 2 plus I 2 by root 2 into 2I by root 2. So cancelling the terms, 2 is 4, again root 2 into root 2 is 2, so 4 by 2 is 2 in the denominator. Here we have limit z tends to z1, 2 denominator, that means 2 into 2 4 by 2, that's 2. Again we can take 2 by root 2 outside there, that is 1 plus I. Now root 2, this is 4 by root 2 comes up, oh sorry, already put limit. So root 2 comes up, I root 2 divided by 4 into 1 plus I is this residue. Now let's find residue at I 3 pi by 4. So residue of f at a raised to I 3 pi by 4 is given by, again this is symbol ball, limit z tends to e raised to I 3 pi by 4 z minus a raised to I 3 pi by 4 into f of z is the residue. So we get same way, limit z tends to e raised to I 3 pi by 4, or we can substitute the value as e raised to I 3 pi by 4 whole square divided by e raised to I pi by 4 minus e raised to I 3 pi by 4, sorry. E raised to I 3 pi by 4 minus e raised to I pi by 4. E raised to I 3 pi by 4 minus e raised to I 5 pi by 4. E raised to I 3 pi by 4 minus e raised to I 7 pi by 4. Now this is 2 by 4 is 1 by 2. So this is e raised to I 3 pi by 2. E raised to I 3 pi by 2 is cos 3 pi by 2 plus I sin 3 pi by 2. Cos 3 pi by 2 is 0 plus I sin 3 pi by 2 is minus 1. So this is minus I. So we got minus I. We substitute minus I here. Now minus these terms. Already now minus all term with e raised to I pi by 4. This minus this gives minus 1 by root 2 minus 1 by root 2 minus 2 by root 2. I by root 2 minus I by root 2 cancel. Next 5 minus 1 by root 2 minus minus 1 by root 2 cancel. I by root 2 minus I by root 2 minus minus I by root 2. That means 2I by root 2. Now minus this term, minus 1 by root 2 minus 1 by root 2, that is minus 2 by root 2. I by root 2 minus minus I by root 2 plus 2I by root 2. So this is the term. Now let's simplify here. This is minus 4, root 2 into root 2 is 2, cancelled with this. So this is minus 2I and take this 2 by root 2 outside. This is minus 1 plus I. So minus 4I divided by root 2 go to the numerator, and this is minus 1 plus I. So residue is minus 4I minus 1 plus I root 2 in the numerator. So minus I cancel. So we get root 2 divided by 4 into minus 1 plus I. Okay. So this is the residue. Now integral over gamma f over z dz is sum of this residue into 2 pi I. So first we got in a raised to I 3 pi by 4 we got root 2 I by 4 into 1 plus I. So root 2 I by 4 into 1 plus I plus root 2 by 4 into minus 1 plus I. Now root 2 by 4 is common. 2 pi I root 2 by 4. This is I into, let's multiply this, cross multiply, minus 1 plus I plus 1 plus I divided by 1 plus I into minus 1 plus I. Sorry, this I term will cancel. There is a mistake. I. Oh yes, here is I. So I and I is cancelled. This I with this I cancelled. So no I term here. Root 2 by 4 1 plus I. Okay, let's correct this mistake. No I here. Okay. So what we get? This is pi I and root 2 into 2 by 4 is root 2 by 2. Now minus 1 plus 1 cancel. This I plus I is 2i. And here is 1 plus I minus 1 plus I is minus 1 plus I square minus 1. So minus 1. 1 into minus 1 minus 1 I minus 1 sorry minus I next I 1 into I square minus 1 okay minus 1 minus 2 I minus I cancel so this is minus 2 now root 2 cancelled and we got 2 cancel pi and this I into I here we have I square is minus 1 cancelled with this negative I square minus 1 and we got pi root 2 by 2 that is pi by root 2. So this is the final answer pi by root 2. That means we got the answer integral over gamma z square divided by z raised to 4 plus 1 dz is equal to pi by root 2. So that integral minus infinity to infinity x square by x raised to 4 plus 1 dx also pi by root 2. So that's it.